Hey guys, so we're going to continue this second chapter that we're in, and this chapter is mainly about what's called functions. Now, in the first lesson, you guys did some linear stuff, slope and lines and things like that, but in general, my hope is that most of what I talk about in this lesson, it's going to be a really quick lesson, but most of which I talk about has been something that's been talked to you guys about before, so it's review. And then we're going to talk a little bit about some new stuff, and that's kind of how most of the year has gone. We've done a lot of old stuff, but we've amped it up a little bit, and then we've added some new stuff, and that's kind of what happens in this lesson as well. So this lesson is all about functions and what a function is and what we do with them. And so I have some terminology and some vocab here that you might want to jot down, but in general, a relation is a set of ordered pairs. Just a bunch of x's and y's is a relation. Like, there's nothing special about them. But a function has something very special about it. A function is a relation. A function is a set of ordered pairs. But the special thing about a function is each input has exactly one output. And what that means, just in general, is if you have some function and you input the number 3 and then you get 5 out of it, the next time you input 3, you better get 5 out again. And the next time you input 3, you better get 5 out again. So basically, every time you input the same number, you should get the same output every single time. That's what a function is. If you would input 3 and get out 5, and then the next time you input 3, you get out 6, that wouldn't be a function. That would be a broken machine. Every time you do the same thing, you want to get the same thing out. In general, inputs are almost always your x values, also known as your domain. And then your outputs are your y values or your range, typically. All right, so the first few questions are just, do these things represent functions? I have a couple of graphs down here. I have a literal set of ordered pairs. This thing here is called a mapping. This is just really showing, if you input 2, -1, and 3, you get 5 and 6 as your outputs. So it's just a different way to express a set of ordered pairs. So is the following relation a function? An easy way to think about it is, it's a lot easier to think about, is it not a function versus is it a function? Like, if I input 2 and get 5, the next time I input 2, I better get 5. And what this is showing is, if I input 2, I get 5. That's perfect. If I input -1, I get 5. That's okay. You can input different things and get the same thing out. That's okay. The only bad thing is if you input the same thing and get different outputs. So this is fine. This is, yes, this is a function. Each input corresponds to exactly one output. Now, if I drew an arrow like this from -1 to 6 or something, if I did this, now if I input -1, I get 5, and if I input -1, I get 6, this is not a function. This would be no if you have one input going to two different outputs. Same thing with a set of ordered pairs. You input 4 and get 2, and then the next time input 4, I get 6, this would not be a function. This is no. Each input does not correspond to exactly one output. Where students tend to go wrong in their thinking is they think if the x value repeats, it's not a function. And that's not true. If I had made this ordered pair 4, 2, you input 4, you get 2. The next time you input 4, you get 2. This is fine. So it has nothing to do with the x value repeating. It's all about, if it does repeat, do you get different outputs? Back in Algebra 1, you probably talked about the vertical line test. That's my hope, the vertical line test. And that's how you can tell if graphs are functions. And I kind of like to treat it as a little vertical scanning mechanism, and I'll explain what it's doing. But basically, if you hold your pen or pencil vertical and you just scan it along the graph, if it ever overlaps your graph twice at the same time, then it would not be a function. It would fail the vertical line test. This, every vertical line hits the graph one time. This is yes. This here, if I go and do my scanning, it fails because, there's a line right here. There's a bunch of them, but there's one vertical line right here that hits your graph at 2 different places. So it fails the vertical line test. So no, it's not a function. What the vertical line test is actually showing is at this x value right here, whatever it is. Let's say it's -1, I don't know. But at this x value would give you this y value here, -1, let's say, and this y value here, -3, let's say. So you have an x value that corresponds to two different y values, so that's why, no, it's not a function. You've probably come across function notation, which I'll explain a little bit about. So this is pronounced f of x, f of x. It's not f times x. It's not like these things are being multiplied, but it's f of x. And again, my hope is in Algebra 1 you came across it, but really all this means is y. F of x is the same thing as saying y equals. But then students each year will say, well, then why don't we just write y equals? Why do we have to introduce some different notation? And the reason that we have to introduce different notation is because it allows us to talk about different functions all within the same problem. You know, it's a name. It's naming the function. This 3x plus 1, its name is f. This second one, its name is g, and the third one's name is h. It allows you to name them, and so what that does is this. If I look at a, so now this says find f of 2. And the way we analyze functions is whatever is inside the parentheses, that's our input. That is what we plug in for x in the function anywhere we see an x, whatever's inside the parentheses here. So f of 2, well, first of all, I know I am using the f function right here. And now 2 is my input, so I'm going to put 2 where the x is right here. So 3 times 2 plus 1. And so that's 7. So the first benefit of function notation is it allows you to name the function. The second benefit is this. I can look at this correspondence right here, and I got 7 as my output, but I can actually make a connection. I know that I get 7 if I plug 2 in. I can actually see the input that corresponds with that output. Whereas if you just wrote y equals 7, you wouldn't know what you plugged in to get 7, if that makes sense. Function notation allows you to see the input-output relationship very clearly. B says find g of -3. So now I know I'm using the g function, the middle one, and I'm putting -3 anywhere the x is, right here. But anytime we have negatives, we need to be very careful with parentheses. Parentheses play a huge role in algebra. So it's going to be 2, and then where the x is, I put -3 squared plus 1. Notice how I write that. The -3 goes right where that x is right here. And now I have to do order of operations. -3 squared, this is positive 9, times 2 is 18, plus 1 is 19. So just be careful with your order of operations. The last one, this might be something new. So you don't always just input numbers. Sometimes you input expressions. And when this happens, this means your output is not going to be a number, but it's just going to be an expression in terms of x. And this becomes a big deal when you go up to your upper levels. You'll start doing this more often. So g of x plus 1. What this means is, in the g function, where I see the x right here, where I see that x, this x gets replaced with x plus 1. I'm inputting x plus 1 in for the x right there. A common mistake students make is they'll leave this x here, and then they'll put x plus 1 behind it. But you're replacing this x with x plus 1. So it looks like 2, and then where the x is, I put x plus 1 squared plus 1. So notice that x got replaced with x plus 1. Then I would like to clean this up a little bit. So I need to square x plus 1. We have to do the parentheses first. And remember, you can't just distribute this 2 because of the plus sign. This is a case where you either need to put x plus 1, 2 times and FOIL it out, or whatever the case may be. I always like to use a little shortcut. When you're squaring a binomial, you square the first term. You multiply the two things together and double it. So like you take the product and double it. So this would be x, so 2x. And then you square the second one. I do this every time I square a binomial. I never write it twice and FOIL it out. I square the first, I take the product and double it, and I square the second one. And then plus 1 is on the end. And then distribute. and then combine. Okay, so again, my hope is that a lot of this is review. This may be a little new right here. And then the very last thing that we're going to talk about, I am guessing, is brand new. And these become pretty big, again, as you go up through your upper levels. And they're called piecewise functions. So I want to graph this piecewise function, okay? Now, it looks very, very intimidating at first. It looks pretty intimidating. You got, different pieces going on. You got inequalities over here. You got function notation. We have to graph. I'm going to try to make this as easy on you as I possibly can, okay? What a piecewise function is and what it means, it's a function, and it's just made up of pieces of other functions. And so a lot of times it might look disjointed, or you have different parts going on, things like that. But again, I'm going to try to make this as easy on you as I possibly can. There's other ways to do this than what I'm going to show you, and some of you will figure out shortcuts. But I'm going to just kind of do what I've done in the past couple years, and it's worked out really well. So for right now, I want to pretend like these bottom two lines don't even exist, and I want to pretend like this inequality doesn't exist, okay? And all I want to do is graph, remember, this is like the same thing as y equals. I want to graph the line y equals x plus 3. That's it. Pretend like nothing else is there, and I want to graph y equals x plus 3. So I put my y-intercept at 3. My slope is 1, so up 1 over 1. Up 1 over 1. You can go down 1, left 1. And I'm going to graph that whole line. Probably should use a straight edge, but I'll trust myself right now. So I graphed the whole line, okay? So nothing big deal. We just graphed y equals x plus 3. But now, here's what these inequalities mean over here, okay? I only want the line x plus 3 only for x values that are less than or equal to 0. That means that for any x value bigger than 0, I don't want this line. I actually want to erase a part of this line now. So here's how I go about this. I go to where x is 0, okay? X is 0 right here, and I go to my graph. And what I'm going to do, I'm going to actually erase either one side of this circle here or the other. I'm either going to erase all the stuff over here or all the stuff over here. Well, I want the part where x values are less than or equal to 0. That means I want the stuff to the left of 0. I want this, which means I'm going to erase all of this stuff over here. So I'm going to go ahead and erase all this. So this right here is the very top piece. This is the line, y equals x plus 3, but only for x values less than or equal to 0. If this was something to keep in mind, if this just said less than instead of less than or equal to, we would actually have an open circle here instead of a closed circle, which we'll talk about. You've done that with inequalities before. All right, we go to the next piece. So we're done with that. Once you finish, you don't need to worry anything about that top piece anymore. The next one is y equals 3. The line y equals 3. Well, the line y equals 3 is a horizontal line crossing the y-axis at 3. And I'm going to draw the whole line. Again, there are easier ways to do this, but this is just, I think, the best way conceptually to make this make sense. So this is the entire line, y equals 3. But I only want this line for x values between 0 and 4. I don't want the whole line. I only want it for where x values are between 0 and 4. So x is 0 right here. So I want this through 4 right here. So basically, I want this line from this circle to this x being 4 right here. I only want this portion between 0 and 4, which means I need to erase all the stuff outside of 0 and 4. Where my pencil is, this is what I want. So I have to erase the other stuff. This eraser's kind of booty. that should be even less dark than it is. Now, here's the deal. We always, if we have just like a segment, a line segment that ends, we either need to put an open circle or a closed circle. We have to bookend it. We have to mark it, is it included or not included? And this is where it's, either equal to or not equal to. Right here at 4, notice how it just says less than, it's not equal to. That means we actually put an open circle right at the end of this line at 4. I know at 0, it's also an open circle right here, but here's the deal. It was already closed. This is the same point as the first piece, and it was already closed. You're never going to have an open circle and closed circle at the same place. Like you won't put an open circle around this closed circle. It's filled in. This point is included as part of this function. And then the last one is y equals negative 3x plus 15. Again, pretend like the inequality is not there. We're done with the second piece. Graph this line. So the y-intercept is 15. The slope's negative 3, so down 3, right 1. Down 3, right 1. I'm going to graph that whole line. Ooh, that wasn't too good. A little curvy. Now, I only want this line for x values greater than or equal to 4. That means I go to where x is 4, here, and I want to erase one side of this line or the other. Now I want this for x values greater than 4, so to the right here. That means I need to erase all the left stuff. And the way you also know, like you can self-check this a little bit, in the end, your graph should be a function. That means it should pass the vertical line test. So like say you accidentally erase this part here, right? Say you erase this part. Well, now your graph doesn't pass the vertical line test. Right here, you would have a vertical line hitting your graph, at two different places. So that also kind of helps you see what you should erase. So I want to erase all this stuff to the left of 4. And so my piecewise function is really just this thing right here. Notice it's a function made up of pieces of other functions. So one thing to point out, they don't have to be connected like this. You might come across one where this just so happened to connect at these two spots. It didn't have to, though. This third piece could have been up here somewhere and done something else. It didn't have to connect. It just so happened to connect on this one. And the last thing, we're going to skip example 5. We're not going to do that one today. But the last thing you could be asked is they could give you a piecewise function and say, what's f of 0? What's f of 3? They can ask about these values from up here. And I want to talk about this. So if they say, I want to start with f of 3. If they say find f of 3, with normal functions, you would just plug 3 in for the x, and then you get your output. Well, the question is, which of these pieces do I plug 3 into? Right? I am going to plug 3 into either this top piece, the middle piece, or the bottom piece. I'm going to plug it in for x, but the question is, which piece? And you use these inequalities here to make that decision. Like, whichever inequality your input satisfies, like in this case 3, whichever one 3 makes true, is the one that you're going to use. So, if I look at the first one, it says that it would be 3 is less than or equal to 0. That's not true. The middle one, 3 is between 0 and 4. That is true. What that means, I didn't make a very good example here because the middle has no x and it is 3. So this kind of sucks, but bear with me. So I would plug 3 in for x in the middle piece right here, and for any x's you see. Now there is no x, so it's just 3. It's just this output right here. What that means is any number I would plug in between 0 and 4, my output would be 3. 0 is a better example. So let's think about which one of these inequalities 0 makes true. 0 is not greater than or equal to 4. 0 is not greater than 0, so it doesn't make this true. 0 is less than or equal to 0. What that means is I plug 0 in for x in this top piece right here. So 0 plus 3 would be 3. So we use these inequalities to decide which piece to plug our thing in. So if I said, I'll do one more. If I said f of 6. So now I check. Okay. No. No. Yes, 6 is greater than or equal to 4. So I would plug 6 in for x here. So that'd be negative 18 plus 15 is negative 3. That's my output. All right, practice your assignment. If you have any questions at all, please let me know.